So today we will have Dr. Atsuhiko Isobe. And Atsuhiko is a physical oceanographer at University of Kyushu in Japan. And he's really keen to understand the behavior of microplastic in the world oceans. And he's now working as a principal investigator of multiple marine plastic research projects supported by Japanese government. He was awarded 3 governmental prizes for the past 3 years. So thanks, Atsuhiko, for joining us today. And we're really happy to invite you today, and floor is yours.
Thank you very much for Nakajima-san for kind introduction for me, and good evening from Japan, my colleague. And today, I'd like to say I'd like to thank all members of this webinar for preparing this great opportunity for me to introduce our work. So today here, I have a plan to introduce our latest work, mostly unpublished in the scientific journals. So as you know, it's difficult to open all results to the internet publicly because this may prevent us from publishing in scientific journals. But I'm pleased to introduce the essence of our recent accomplishment as much as possible of this webinar. So today I prepared 2 topics. One is the global mapping of microplastic abundance in the upper oceans. So this is based on the microplastic observation in the ocean to date by many researchers over the world oceans. So I try to make a 2-dimensional mapping. 2-dimensional mapping means mapping in the uppermost layer of the ocean of the microplastic abundance. And a second topic is the fate of missing plastics. This is very, very famous paradoxical phenomenon in marine plastic research. By using the second topic is made by using numerical modeling, validated by the global mapping shown in the first topic. Okay, before showing our result, I briefly explain the background of our research. The background of the global mapping is shown in this panel. So microplastic observation date back to 1970s over the world ocean, but probably the famous observation over the world ocean has been published by Erickson and Kozar 2014. But it's sometimes difficult. We made difficulty to compare or to synthesize these datasets because these datasets use a different metric or different unit. For example, now Erickson provided his data with the metric of distance, particle count per survey areas, and Kozar showed weight per survey areas, and in addition, their meaning of the survey area are different. Nearly the same time, we publish the mapping of the microplastic abundance in the surface layer around Japan Island. In this case, we use the particle count by volume of the seawater measured directly by flow meter. So, this is directly obtained by the surface net towing. Also, this data is very difficult to directly compare with the previous 2 results. So apparently, we need the freely available data set of the microplastic abundance in a harmonized metric or harmonized procedures, harmonized method over the world ocean. In the first topic, I'd like to introduce our latest work regarding this global mapping of the microplastic abundance by integrating the observational result by many researchers to date. A second topic is the fate of missing plastics. This is a very famous paradox. So 2014, according to the Erickson 2014, they showed the total mass of the drifting marine plastic is about 250,000 tons over the world oceans. So we met many big gaps between the total amount of the mismanaged plastic waste on land provided by Jambek. She provided us with 30 million tons per single year. Thereafter, Leverton and Schmidt estimate the total amount of the plastic waste released from each river over the world ocean about around 2 million tons per single year. So this is, we have met a very big gap between the microplastic found in the actual ocean and plastic debris actually found in actual ocean and plastic waste on land or plastic waste released from rivers. So the difference is called missing plastics. So of course, we understand that it's sometimes difficult to accurately estimate the total weight of the plastic debris in the ocean because this value is mostly observed visually on vessels. So the accurate estimate is very difficult. And also in estimating the mismanaged plastic waste on land or plastic waste on river has many options in accurately determining these values. So it's sometimes difficult to accurately observe all values in this panel, but the missing plastics is also found in the size distribution. Probably in understanding, this is firstly pointed out by Kozaru in his paper. But I use our data set to introduce, to explain these missing plastics. In the, in the right hand side, I'm showing the size distribution of the microplastic collected around Japan to date. Probably during 5 years, we use all data. We use all microplastic data to depict this graph bar chart. And bar chart means bar chart means the piece per cubic seawater volume, cubic meter, the seawater volume, and horizontal axis means the fragment size of each microplastics. We can find that the amount of the microplastic increase as we move to the smaller size. This is natural because microplastic decrease their size and increase their number in fragmentation as shown in the upper right panels, upper right cartoon. So on red curve means the expected curve of the size distribution by considering the mass conservation through the fragmentation processes. So we compute the total mass of the microplastic with a size of 5 millimeters at first. Thereafter, we compute the amount of the plastic waste as we move to the smaller sizes. We can find a large gap between the actual observed microplastic abundance and expected curve. So this missing plastic may be removed from the upper layer and may, as I show later, this probably settle down to the abyssal ocean or absorb into the sandy beach or anyway, it's removed from the upper oceans. So we try to understand, by using the numerical model, we try to understand the fate of these missing plastic. This is our latest job, latest work. So first, I'd like to talk about the global mapping of the microplastic abundance in the upper oceans. So fortunately, microplastic observation, according to the regarding the microplastic observation, we have a very well-organized guideline at the present time. These two guidelines is the latest guidelines protocols. Right, let's show the guideline published from Ministry of Environment Japan. Corresponding author is Professor Michida, University of Tokyo. And right is the guideline published from GESAM this year. So according to this guideline, we have to use to monitor the microplastic in the upper layer in the ocean. We use the surface net tool using Newton net or Manta net. The net size is probably mostly large, around 0.3 millimeter, and we have to use the fluorometer to measure the CO2 volume passing through the net. And we have to use the density separation to extract plastic fragment, or we need chemical treatment to remove organic matter. And spectrometry, for example, using the FTIR or Raman spectrometer to identify the plastic polymers. And detailed procedures have also provided by our recent papers. So using these, in strict terms, some work is not used this protocol, but mostly recent work used these procedures. So we pick up the recent observation. We pick up the observation of the microplastic over the world ocean these 20 years from 2000 to 2019. So in total, about 3,000 surface net toll in the world ocean were found. This study including both published and unpublished data. The published data is found by literature surveys, or unpublished data is provided by our co-authors in this paper being in preparation. So we have about more than 100 observations over the world ocean each year during these 20 years. And we have observation monthly, even in midwinter. And using these, we try to integrate these observations. Okay, this is the location of the observation, and color means the particle count observed directly by the Newton net or Manta net. The unit is so that unit is piece per cubic meter. So dense observation are carried out around the United States, and ocean surrounding European countries, ocean around East Asian follows. But we have not so large data set in the mid-ocean of the Atlantic and Indian Ocean and Pacific Oceans. And thereafter, we have to process these raw data because, as you know, the microplastic is mostly made from the polyethylene or polypropylene rather than CO2. So this means that the vertical distribution is very sensitive to the oceanic condition. The figure on the left-hand side shows the vertical distribution of the microplastic abundance provided by the SF 2015. So we can find that the microplastic vertical profile of the microplastic abundance is mostly followed the E-folding curve like this, according to the Kukuruka. The W means upward terminal velocity of each microplastic fragment. Now, in this study, we used 5.3 millimeter per second as according to the research experiment. And A0 means the vertical diffusivity, and vertical diffusivity is computed from the K means von Karman constant, and HS means the significant wave height. And also we need the frictional velocity by using the wind speed. In this study, we use wind and satellite derived winds at the date of that location where and when the observation conducted. And HS significant wave height were computed by a wave model driven by the satellite-derived winds. And thereafter, we vertically integrate this in exponential curve. We vertically integrate this exponential curve from the surface to the infinitely deep layers so that we obtain the M. M means the total particle count in a water column in a unit of particle count per areas. So N0 is observed value directly obtained by the by towing the Newton net or Manta net. And if we have HS and W10, That's mean the wave height and wind speed. We assume the upper terminal velocity. We can obtain the total particle count, which is independent of the oceanic condition, because this is already vertically integrated. And thereafter, also we need another kind of the data processing. We have to we try to convert the particle count to weight, because some ecotoxicologists or environmental chemists sometimes use their weight in counting the microplastic abundance, because in their laboratory-based studies. So we try to convert particle count to the weight. This figure shows the size distribution again, and we assume the size distribution in this curve, exponential curve. Beta and alpha is the empirical coefficient obtained by the observations, and delta means the size, just size. So by integrating this curve in the entire size, we can obtain the entire the total particle count, and by assuming the cylindrical shape by each fragment with a size delta as a diameter and thickness is 0.1 or 0.4. So this is a very thin cylinder shape. So assumption of the this cylinder shape of each fragment and assumption of the size distribution like this, we can obtain, we can so convert from total particle count to the total weight of the microplastic with the size distribution assumed by this curve. A detailed procedure has been already published in by our Nature Communication paper last year. Okay, this here shows the total particle count in the upper panel and the weight in the lower panel in both columns over the world oceans, obtained by many researchers, including the published or unpublished data set. So we can find very dense microplastic concentration in this area. In this area is so-called North Pacific garbage patch, and we obtain the dense microplastic in the Mediterranean Ocean, the ocean around the European countries, or ocean in the East Asian countries. And thereafter, we changed this data set to the gridded data set. In this data, the abundance is again returned to the milligram per cubic meter. So in this to create this data set, we use the averaged wind and averaged waves height. And thereafter, the total particle count in the water column return to the surface concentration in the uppermost layer in each month. So you use the average wind speed and average wave height to compute the microplastic abundance in the layer in each month. I hope this animation is smoothly moving on your computer. Okay, and so I think that this map is very friendly to understand for the understanding the microplastic distributions. And we have dense microplastic in mid-ocean, along the oceanic front in subtropical gyres in Atlantic or Pacific or Indian Ocean, and we have dense microplastic concentration in the ocean surrounding European countries, including the Mediterranean Ocean, and we have a very dense microplastic around Japan Island here. And it's surprising, for me, it's surprising that the relatively dense microplastic is revealed in the ocean, in the Antarctic Ocean, in the northern oceans. And the microplastic concentration of the microplastic in summer in northern hemisphere is larger in the microplastic concentration in winter. This is very natural reason, because the microplastic abundance in the surface layer increase as ocean conditions change to be calm in summertime. Okay, now next we move to our numerical modeling result, but this result is very useful for validation with numerical model. Okay, I would like to introduce our numerical model result to elucidate, to unclear the fate of missing plastics in the oceans. And so our model is basically the particle tracking model, like this particle tracking model, but with the symptom as shown later. I will explain later. But it's not usual particle tracking model because we have four kinds of the particles in this model. One is the microplastic in the ocean, which is directly released from the river mouth over the world. And we have microplastic on beaches. So exchange occur between these microplastic in sea and on beaches, those on beaches. The time scale for the exchange is tau1 is tau2. The tau1 is the time scale for moving onto beaches from sea, and tau2 is the time scale for redrifting into the ocean from beaches. And each microplastic, each particle has. Sorry, I forgot to explain. This tau is the e-folding scale of the just e-folding scale of each plastic of the age, and each microplastic, each particle has each tau at a point along this e-folding curve. And tau1 is 1 day, and tau2 is 400 days assigned to for each tau. This value is the experimental value obtained by the Kataoka 2013, published in Marine Pollution Bulletin. And likewise, we can we set two kinds of the microplastics. One is the microplastic in the sea, and one is the microplastic on beaches. And these two microplastics exchange each other with the time scale tau3 and tau4. Tau3 is time scale for moving onto beaches from sea. Tau4 is the time scale for moving from beaches to the oceans. And tau3 and tau4 is 10 or 30 days as shown as found by the Hinata 2017 and 2019. This work is also published in Marine Pollution Bulletin. This time scale is the observed values in the actual ocean on beaches. And this large microplastic change to the these macroplastic change to the microplastic in the model. So macroplastic change to the microplastic with a time scale of tau5 by the degradation or fragmentation. So as you know, at the present time, it's very, very difficult to determine this tau5, the time scale for the fragmentation at the present time. So this is one of the challenging topic with the cooperation of the polymer scientists. Now we have many options. We use the variety of the tau5 from 1 to 10 years. And as you know, all plastic fragments is not heavy plastic. The mostly microplastic is made from the polyethylene or polypropylene related to seawater. So according to the production rate at the present time, we assume that 50% of the macroplastic change to the microplastic after fragmentation in the model. So remaining macroplastic of the 50% remains at the place where this conversion from macroplastic and microplastic occurred around the beaches. And a fragmentation rate is 10 times for the macroplastic on beach than microplastic in the sea. And microplastic in the sea or microplastic on the beach removed from the upper ocean or beaches. Of course, also this time scale is also difficult to determine at the present time. It's very difficult, it's a very challenging topic in the microplastic ocean plastic research. For example, Isobe 2019, we assume that this time scale of 3 years by comparing the modeled and observed microplastic distributions. In the present study, we assume that we assume the variety of the tau6, the time scale for the removal rate from 1 to 10 years. A removal process is very difficult to explain at the present time. This includes, for example, the mixing vertically from upper layer to the deep ocean by wave breaking or laminar circulation or something like that. These physical processes or biochemical processes, including the biofouling and vertical migration after the aggregate, including the aggregation and something like that. Okay, this is the emission of the, this view shows the emission of the microplastic. This model starts from the release of the microplastic from big rivers over the world ocean. We use the Reverton data set provided by the Reverton 2017, published in Nature Communications. And he provides the amount of the mismanaged plastic waste from each river over the world ocean at 2010. And we assume the time series as this time series parallel to the GDP of each country where river mouth exists. So our emission model is the Reverton and GDP model. So models start from 2061 and ended to the 2017. This means this is at the present time in study. So during 57 years. So initial condition is of course zero plastics. We have no plastic in the ocean. In total, we release the plastic debris, microplastic from the river, 21.4 million tons over the entire computation period of this model. On the background, in the ocean or above the ocean, we give the wind and ocean current and waves. So wind vector are used. The data set obtained by a multiple satellite. This wind is used for windage of the macroplastic and driving force of the wave model to compute the Stokes drift as shown in the lowermost panel. And before 1993, we used the monthly average value, and this monthly average value was updated every month. After 1993, we use updated every month in each year. And with the ocean current provided by HiCom in the uppermost layer, our model is just two-dimensional model in horizontal space. So all microplastic and macroplastic move horizontally in the uppermost layer. And we use the Stokes drift. And this Stokes drift is added to the ocean current to compute the transportation of the macro and microplastics. Stokes drift are computed by using the University of Miami wave model. And these all wind and current are updated every month, every time step. I hope this animation moves smoothly on your computer. And this figure, this movie in the lower panel, and this then the panels in the upper three panels show that a result of the motion of the macro and microplastic in the beginning of our computations. Blue dot means a macroplastic directly released from the river mouth in over the world oceans. And yellow dot means the microplastics generated by fragmentation of the macroplastic in the model. So you can find that the moving macro and microplastic and some microplastic and macroplastic are washed ashore along the beach. Sorry, I forgot to mention. This is a result of the model with diurnal fragmentation time of 3 years and removal time scale of 3 years. So we have so many options. In this presentation, we have only shown this case. And this figure shows, this movie shows microplastic distribution in the upper panel and the macroplastic distribution in the lower panel. And again, and the result is shown of the result of the model with both time scale of 3 years, as shown here. You can find that both macro and microplastic are very, very dense in the Asian area because plastic release of river are very huge in these areas. And a huge amount of the macroplastic move from Africa to South America, also found in the lower panels. Okay. This result can be compared with mapping of that I've shown in the first topic. Lower left panel shows the abundance of the microplastic in observation shown by the gray bar, and microplastic abundance shown in the black boxes. You can find that the both very comparable with each other. So honestly, to be honest, the result of the spatial variation is not well reproduced. So microplastic observation, we compare the microplastic observation in 5 areas in the area in the East North Pacific and North Atlantic, South Atlantic, and East Indian Ocean, Western North Pacific. As you can see in the lower right panel, the microplastic abundance in the Atlantic Ocean is underestimated. I'm not sure the reason, because the microplastic release from the European countries and the countries surrounding the Atlantic Ocean is not so high compared with the Asian areas. So the lower amount of the microplastic abundance is reasonable, but in reality, abundance of the microplastic in the Atlantic is relatively high than we might have imagined. This summarizes our model result, and we estimate the percentage of the plastic, fate of the plastic to macroplastic in ocean, and macroplastic on the beaches, and microplastic in the sea, and microplastic on beaches. So you can find that as I told you, in total we release 21.4 million tons of the macroplastic in the ocean from rivers. And in our computation, macroplastic in the sea account for about only 2.1%. And the macroplastic on beaches account for 14.2%. And we remained the microplastic made from heavy plastic. It's not drifted in the ocean, it's about 41.8%. This remain on beaches when they convert from macroplastic to microplastics. And the ratio of the microplastic in the sea is about 3.2%, and microplastic on beaches about 8.3%. And total amount of the microplastic removed from the upper ocean is account for about 31.4%. This is the fate of the microplastic in the model. And interesting is that the plastic debris remaining on land. As I said, our model shows the microplastic abundance comparable with the observations, as shown in the upper left panel. And abundance of the macroplastic abundance in the present model is about 450,000 tons. It's comparable with the estimate obtained by the Ericsson 2014. So this suggests our model is reasonably work to reproduce the microplastic or macroplastic in the actual ocean. And the important thing is a model, the amount of the plastic released from river provided by the Riverton and GD model works well in reproduce the particle release in the actual in the reality. Our model showed that the 21.4 million tons are released during these 57 years. But we have met again we have to be wondering this very big difference between the particle release from river and mismanaged plastic fragment on land. According to the Jambeck, mismanaged plastic waste on land is about 30,000 tons per a single year. If we count this so mismanaged plastic waste during this about 60 years may increase to 300 million tons, 300 million tons during these 57 years. So this is much larger than the plastic release from the rivers. So the huge amount of the plastic must be remain on land. We have not trace of this mismanaged plastic, missing plastic on land. I'm thinking that I'm thinking of this missing plastics as absorption into land soil or stock in territorial water or plastic debris in the air. But we have this so this is very a new challenge, and that to find this missing plastics.
So first question is from Anonymous. How do you count for the microplastic particles smaller than your mantle to mesh sizes?
Yes, this is very important questions. So microplastic defined in my presentation has the limitation in size. So microplastic in our presentation means the microplastic with a size larger than 300 micrometer and less than smaller than 5 millimeter. This is the upper limit is the definition. So the smaller microplastic than the mesh size is not our target, both in observation and modeling. So this tiny microplastic in modeling, in monitoring is our new challenge. This is very important, but this work and this small tiny microplastic is not computed or monitored. Okay, and next is.
Okay, thank you. Yeah. Okay, so next question is from Delphine. And thanks for your excellent talk. Could you briefly explain the interpolation method from Dr. Kako you use?
So we use the optimal interpolation method. This method is widely used in oceanography or meteorology to make gridded data. Where so the procedure is so interpolation. This is just interpolation, but the technique should be provided in so papers in detail. It's difficult to explain briefly for me.
Okay, thank you. Okay, we have question from Victor. Asking for the research spectrum, e-folding timescales are from the Hinata and Kataoka papers, but how did you select the beaching timescale?
Yeah, this is very important and very good questions. So this is Kataoka and Hinata. Their experiment is to estimate the residence time of the macro or microplastic on beaches. So strictly speaking, they estimate the time scale for macro and microplastic from beach to the oceans. So now we have assumption that so equilibrium state in short time scale between so microplastic from beach to the ocean or ocean to the beach. These two process is balanced in short time scale. To accomplish this equivalent state, we can estimate the time scale from ocean to the beaches. So yes, this is a very important point. We need assumptions for the equilibrium state. So this is detail is also again I have to say detail is provided by the paper of the Professor Hinata. I think this is very excellent papers.
Okay, thank you. Okay, so now we have a question from Prabhakar asking, how did you explain the difference between the observed plastic in the ocean by Japan and the very low estimation of mismanaged waste from rivers, which is Labraton 2017?
Sorry. How do you explain the difference between the ocean plastic in ocean by Japan? Yeah. This is very important. This is very important and interesting point. As you say, the particular plastic release around Japan Island is not so large in comparison with other areas, but Japan Island located in the downstream of ocean current. And plastic release from Asian countries and Southeastern countries are relatively large. So these large plastic moved to the area over the East Asian area. So the ocean surrounding Japan, in the ocean surrounding Japan Island, the dense concentration of the macro and microplastic is become very large. And interesting is that so microplastic concentration in the ocean around Japan Island is larger than the concentration around China. I think it's very interesting. So I guess this situation may suggest that the macroplastic wash ashore on the beaches around Japan Island and thereafter change to the microplastics. So microplastics are so largely and very so frequently and very so largely generated around Japan, around the in the beaches around Japan Island. This is one of the suggestions in our monitoring by our monitoring results. Thank you very much. All questions, very interesting point.
Okay, thank you. So we got a question from the same person, private vehicle, and asking, estimated microplastic quantity in Bay of Bengal seems to be high. What percentage remain in the bay, and is it possible to quantify the residence time?
Bay of Bengal. I did not see the detailed distribution by each bay or each marginal seas, but bay, in my understanding, the concentration, high concentration of the Bay of Bengal is made from the macro or microplastic transport from the South China Sea passing through the some strait, Indonesian straits by Indonesian through flows. So I'm not sure there is why the dense concentration of the Bay of Bengal maintains throughout the year, but I guess I found that the circulation, a gyre inside the Bay of Bengal is very intensively found, and plastics, marine plastic trapped inside the gyre inside in the Bay of Bengal. This may one of the result to enhance the concentration of the microplastic or macroplastic in the Bay of Bengal. Yeah, it's very interesting to see the each result of the each regions because of the resolution of our model is 10 kilometers. So Bay of Bengal is also the reason we can resolve this each bay, such as the Bay of Bengal. Thank you very much.
Okay, thank you, Atsuhiko. Okay, we have another question from Emily. Thank you for presentation. Near coast areas where there is low surface microplastic abundance are areas with no microplastics or no observations?
Sorry, I did not explain. My answer is no observations. No observations. You can find the white. You can find the white area in my presentation. Can you see this one?
Yeah, we can see that.
Yeah, and yeah, we have so many area with that color. In this color, we don't have any observations. We cannot make a gridded data by interpolation because of this very sparse data set. So we have to make an observational network as an intergovernmental effort, international effort. Thank you very much for these great questions.
Right, thank you. So we got more questions. It's from, apologize for my pronunciation of the name wrong. I do my best. Genzari Yosura, asking, thank you for this informative talk. So can you say all or almost all the plastic or microplastic found at the water column comes from the beaches, landfill or landfill?
Almost all plastic or microplastic found at the water come from the beaches. No, I forgot to say. I had to say that the part of the plastic debris came from the ocean or generated in ocean. For example, the fisheries activities. So this model did not include the oceanic plastic debris, oceanic generated plastic debris. And but mostly probably is that the amount of the oceanic debris is about 20% or less, according to previous studies. So I believe almost all plastic debris can be explained by the plastic debris from the landmass, especially from the river mouth.
Okay, thank you. So we still have 5 more minutes. We got question from Delphine again, which is, so she's asking, so basically we study the current to know how the microplastic drift from the beaches into the water. Oh, it's different. Okay, sorry about that. I'm repeating again. So basically, we study the current to know how the microplastic drift from the beaches into the water column to they sink in the seafloor. What do you think? What do you think about that?
Yeah, this is very great questions. So I have this. So ocean plastic circulation. We have to elucidate, uncover the entire ocean plastic circulation. Otherwise, we cannot predict the future ocean plastic pollution, or even in the current status, we cannot understand how the microplastic distribute in our oceans. So, but probably the difficulty arises from the observation is very sparse, especially with the microplastic abundance in the water column. For example, we probably, I guess, a very tiny microplastic drift even in subsurface layers, even in several 10 meter or 100 meter or 1,000 meter in the oceans. But the observational results are very sparse at the present time. So at the present time, we cannot establish the numerical model to reproduce this kind of the motion of the microplastic in the oceans. But we need much more observation in the subsurface layer of the oceans to uncover the distribution pattern of the tiny microplastic in the water column, and of course the sea floors. Yeah, challenge is to uncover the ocean plastic circulation entire ocean, including subsurface layers. Yes, it's very important. Someday I want to make a 3-dimensional numerical model to reproduce the entire ocean plastic circulations, including the biological processes. This is my future target. Thank you very much.
Yeah, thank you, Atsuhiko. Yeah, we're really looking for the 3D modeling with bioflowing. Okay, so we got 2 more questions. The next question from Delphine. You use a removal timescale of 3 years from the surface and beaches. How does this differ from the on the order of days of beaching and resuspension?
Differ from the on. Yes. We use the removal timescale of several years. So this is according to our study. So in our study published last year in Nature Communications, so we compare the microplastic distribution observed actually in the ocean and those modeled in the computer, and we have to remove the microplastic in the model with a time scale of 3 years. Otherwise, we cannot reproduce the the oceanic distribution actually observed in the actual oceans. So the order of the year is possible. I think the order of the year is possible, reasonable. Order of the days, or the order of the several 10 years is too short or too large, too long to evaluate the removal time scale. Of course, we can understand we have so many options. So we have to investigate the different time scales. This is just my suggestion at the present time. So I'm thinking of that order of year is most reasonable to think that reasonable time scale.
Okay, thank you. Okay, here is the final question of this talk. It's from Thierry, asking, thanks for sharing very interesting new result. What are the largest uncertainties in your model? The surface velocity, transfer timescales, or fragmentation processes?
Yes.
What do you think?
So we have so many options. We have so many unknown parameters, but the most important and most difficult parameters to determine at the present time is removal time scale and fragmentation time scale. Probably removal time scale should be elucidated by the cooperative work by oceanographers or geologists or so the variety of the researcher with a variety of background, and fragmentation time scale should be uncovered, should be investigated by the collaboration of the our oceanographer and polymer scientist. So this is a new challenge. And these two timescales most I have most concern, and it's very difficult to determine uniquely at the present time. So it's very important questions. Thank you very much.
Yeah, thank you, Atsuhiko. We really enjoyed your talk, and thanks everyone for joining us today.